Hey everybody, this is Mr. Cure. In this video, we're going to be looking at states of matter for elements and compounds. So what I have in front of us here is one of my favorite reactions. It's the reaction of gummy bears and potassium chlorate. So this reaction is very vigorous. It's called Hell of the Gummy Bears. Let's actually check out the reaction, see how amazing it is. Here we go. You can see why it's one of my favorite reactions of all time. So what's going on here is actually a really cool set of reactions. And ultimately, basically what's happening is we have a decomposition of the potassium nitrate into something that's causing the reaction. We'll be looking at that at the end of this video. So let's look at the periodic table first of all, because you have to know the states of elements in order to even do any states in any kind of chemical reaction. You can look at all the elements, they're all solids with a few exceptions up in the corner. So most elements are metals, and most of the metals are going to be solid. There are a couple of exceptions. You're going to have liquid mercury over here, but the rest are going to be metals. Now the non-metals are going to be mostly gases. You have a whole bunch of these gases all down here, the noble gases, nitrogen, oxygen, fluorine, chloride, even hydrogen over here. Don't forget about that. Some exceptions though. Bromine is going to be a liquid, and then iodine, astatine, sulfur, phosphorus, silicon, aluminum, boron, these are all going to be solid. So how do we know? Well, we have a set of rules to help us figure this out. Now you saw these rules on the bottom of the intro to chemical reactions handout. So as we said, all metals at the beginning are going to be solids except for mercury, which is a liquid. Non-metals are mostly gases. So Hofbrinkels are gases, except for bromine, which is a liquid, iodine is solid. Noble gases are obviously gases, and other nonmetals can be considered solids. So that is it for elements. Now, how about this? What do we have here? Well, this is one of the reactions we saw earlier. This is the burning of magnesium. So you have magnesium. Remember, it's going to be a solid metal. And you're going to be adding oxygen, which we know is going to be a gas, and it forms this magnesium oxide. Look at this. The magnesium oxide looks like it's going to be a solid. How about this reaction over here? What we have here is the reaction of iron, solid, plus oxygen, and what it forms is Fe2O3, or iron 3 oxide. And again, this is going to be a solid. This is rust, and the oxygen is a gas. So it looks like metal oxides typically are solids. Okay. How about this? Well, what I have here, I've got the combustion of sulfur on this side here. So sulfur, which is a solid, remember it's a non-melt, it's a solid, plus oxygen, gas, and it gives us this sulfur dioxide. And look at it, it looks like it's some kind of, yeah, it looks like it's some kind of hazy gas there. So it looks like it's a gas. And here, we've seen this before as well. We're gonna have carbonic acid. That's what makes carbonated beverages, right? Here we go. And it's aqueous. It comes, and what happens is you open up a bottle of carbonated water or pop or something, and what happens is we have a decomposition reaction where you're going to have water being formed plus carbon dioxide gas. Oh, interesting. So here it looks like that all of these non-metal oxides are gases. And in fact, those are the rules. So go back to your handout. So on your handout, rule number 2 and 4. Metal oxides are solids, so magnesium oxide, calcium oxide, iron 3 oxide. Maybe add some of these examples to your worksheet. And non-metal oxides are gases, so sulfur dioxide, carbon dioxide, etc. All right, let's look at the other rules. Now, how about ionic compounds? Well, at room temperature, ionic compounds are solids. And the reason is we've got this crystal lattice, which is made up of our ions, right? So we're going to have our sodium cation and chlorine anion. and they are super attracted to each other. Very high attraction between these ions, and that gives us a solid in this crystal lattice. Well, what happens when we add this to water? Well, when we add this to water, the water molecules come in and they overcome the attraction between the ions. They separate them. We call that dissociation. And then the water molecules, remember, are polar because of their polar bond. The partial positive ends surround the anion, the chlorine ion, and the partial negative ends, they're going to be surrounding the sodium cations. And we've got this aqueous solution, AQ for aqueous. So let's look at our summary. So at the bottom of your page again, rule number 5, I'd like you to add this in here. Solids at room temperature for ionic compounds because of the strong interaction between ions. In solutions, most of the time they're soluble, but not always. So you have to look at these solubility rules. So keep that in mind. You have to always check those rules for ionic compounds and just see, are they soluble or not? So you know how to use those. And finally, you might want to put that on this diagram just to kind of show what's happening at the molecular level with solutions of ionic compounds. All right, finally, we've got molecular compounds. What the heck is going on with them? Well, remember, molecular compounds, there's a lot of variation. And the reason is it's all because of polarity. So what we have here, we've got 4 different compounds. I've got oxygen gas. Here we've got hydrogen chloride gas. And then here I've got water, which happens to be a liquid. And finally got glucose, which is a solid. So we have a whole range of states here. Why is that? Well, what happens is we have to look at the intermolecular forces between molecules. That determines the state. So for example, if I look at oxygen, there's no difference in electronegativity. We have a perfectly nonpolar bond, so it's very, very low attraction. In fact, there's just a little bit of London dispersion, and that accounts for the super low melting point of minus 219 degrees Celsius. Well, let's look at hydrogen chloride. Hydrogen chloride, well, we've got some electronegativity difference. It's over 0.5, less than 1.7, so it's a polar covalent bond, giving us a polar molecule with partial positive and negative ends. And because of that, the opposite poles here, dipoles, attract each other. And that's why the melting point's a lot higher than it is for oxygen. So here we have dipole-dipole interaction, remember, from the last unit. And how about water? Well, water is the same thing. We have a larger difference in electronegativity, so there's a lot more attraction here between the charged dipoles. It's a special dipole-dipole interaction. Remember, this is called hydrogen bonding. So hydrogen bonds are a very strong type of dipole-dipole. And finally, what's going on with sugar? Sugar, the melting point is 146 degrees Celsius. Well, if you look at sugar, it has a lot of oxygen hydrogens in here. And the oxygen hydrogen, just like in water, has a difference electronegativity of 1.2, giving very high delta positive and partial negative charges here. And because there's so many of these within one molecule, there's a lot of interaction in any particular molecule. So let's look at this one. The oxygen is going to be attracted to the hydrogen. This hydrogen is attracted to this oxygen over here. Here we have this oxygen interacting here, another one over here. Hydrogen interacts over here. So you can see there's a lot of interaction between these two adjacent glucose molecules, giving us a very, very, very high melting point. So on your handout, I'd like you to add rule 6, where we have got molecular compounds where the state varies depending on the polarity and strength of the intermolecular forces. So remember, London dispersion are weaker than dipole, should be dipole here, pardon me, and they're weaker than hydrogen bonds. So that gives you an overall idea that molecular compounds have a lot of variability. So it's hard to tell what the state is, but you'll know the common ones like water, oxygen, ammonia, things like that. Okay. Now, let's go back to the decomposition of potassium nitrate. What the heck is going on over there? Well, let's check out a quick video to see. And you can see here that we're going to be melting the potassium nitrate. That's one of the key things that has to happen. Eventually, it's going to melt. And we're going to take a splint, we're going to light it on fire, then put it out. So now it's a glowing splint. If you put the glowing splint inside, what's going to happen? Well, put it in, and after a few seconds, here we go. Yes, it's going to happen. All right, there we go. The glowing splint ignites. So we know that we've got oxygen gas being produced. Now, after you let the molten compound cool down, you can see, hey, there's something left behind. It's going to be an ionic compound. So let's look at what this actually is. Look at the actual reaction. Again, this is a little bit of fun, just so you know what's happening behind the scenes. So again, what's going on here is we're going to have potassium nitrate. Now, potassium nitrate is a ionic compound, so we know it's going to be solid. And it's going to break down into oxygen. Remember, we saw the glowing splint test, so oxygen gas. And whatever's left behind, well, we also have an ionic compound. So we have potassium, we have some nitrogen left over, and also a little bit of oxygen. So potassium nitrite, and remember, it was a solid, right? It's an ionic compound, solid at room temperature. And then you do a little bit of balancing here. So you're going to say, okay, I'm going to have balancing. So we put 2 here and a 2 here. We have 2 potassiums, and we have a nice balanced chemical equation. And that's what it's all about. So when you're looking at states, it's important to understand what the states of the reactants are at the beginning and also of the products at the end. So it's a nice summary for you. You'll be probably referring to this chart quite a bit later on as we're completing chemical reactions. Anyway, that's it. Take care, folks. Yes.